Hi there, and welcome back to another review session for your final exam in Calculus 3208, presented by CDLI. Today we're looking at some applications of trig functions in the calculus that deals with them. Specifically, we're going to look at some optimization and some rectilinear motion, or motion stuff in general. There's some projectile stuff there as well, so lots of fun. Let's get going. So we're going to look at motion, optimization, and trigonometry. So we're going to solve problems. That's what we do best. Where trig functions model particle motion, and then we're going to find maximum, minimum, can't speak today, values for a trig application as well. All right, so let's take a look at our first problem. Particle is moving on an x-axis, so its displacement is given as a function of time by this stuff. Okay, so t is in seconds, and s is in meters. All right, so let's take a look here. Find and interpret the particle's velocity at time t equals 3. Well, we should remember velocity function is the first derivative of the position function. So what's that going to give us? Derivative of the first, which is a t here on a product rule, will be a 1 multiplied by the second, which will be sine of pi t. Plus the derivative of the second stuff will be cosine, and then we're going to need chain rule with that pi, so we just will take the pi now. So we get pi cosine of pi t, pi, and then we're going to multiply that by the first function, which was t. Okay, so we can clean that up a little bit, but I'm going to write it over here because I know we're going to need it for part B as well, because, hey, I made up the question. So we've got v of t equals sine of pi t and plus pi t times cosine of pi t. Okay, let's hang on to that for a second. Now, we want to figure out how fast is this thing moving at time equals 3 seconds. So that's going to give us sine of 3 pi plus pi times t will be 3 pi multiplied by cosine of 3 pi. Alrighty, so what's that going to give us? Well, sine of 3 pi I do believe is equal to 0. So that's gone. And then we've got 3 pi times cosine of 3 pi, which is negative 1. So we're going to be moving at negative 3 pi meters per second. So v of 3, just found out, minus 3 pi meters per second. You can calculate that with your calculator if you like, but we'll go with an exact value for now, because I'm mostly interested in part B here. That'll be about 10-ish, but it doesn't really matter much. So let's ditch all this. We already recorded all the important stuff that we needed. And let's try part B. It says, is the particle speeding up or slowing down at this time? So that's an issue of acceleration. Now, don't be fooled. Just because acceleration is positive or negative doesn't necessarily tell you right away whether or not your particle is speeding up or slowing down. It depends on which direction you're moving. So if you're moving in the negative direction and your acceleration is pointing in that direction as well, you'll be speeding up. But if they have opposite signs, then you'll be slowing down. So let's see what our acceleration is here. So let's remember that acceleration is the second derivative of position, which is the derivative of velocity. So over here, the derivative of sine of pi t is going to be pi times cosine of pi t. Okay, and then we have to differentiate this bit as well. And the derivative of that bit will be, let's give ourselves lots of room. So we're going to have plus, this is a product rule. The derivative of the first bit, which is pi times t, will just be pi. And the derivative of this, multiplied by the second bit, which is cosine pi t. And then the derivative of the second bit will be, let's see, negative sine, so negative pi sine of pi t, multiplied by the first bit, which we already knew was another pi t. Alrighty, so putting all this together, these two terms are identical, so let's take 2 of them. So 2 pi cosine of pi t, and then we're going to have plus, it's negative pi squared t times the sine of pi t. Okay, so that's nice. So if I let t equal 3 now to find my acceleration at time 3, I'm going to have 2 pi times cosine of 3 pi minus 3 pi squared times the sine of 3 pi. Whoop, not 35, 3 pi. Sometimes the hand and the mind are not doing the same thing. All right, so what's that going to give us? Let's see. 2 pi times cosine of 3 pi. Well, we already said cosine of 3 pi was negative 1, so this is negative 2 pi. And then over here, 3 pi squared times stuff that equals 0 is going to be 0. So we got negative 2 pi meters per second, or meters per second squared. So since our velocity and our acceleration have the same sign, we are actually speeding up here, not slowing down, even though we're going in the negative direction. Don't be fooled, you're speeding up. Okay, let's move along and try another one. So example 2 here says, when a projectile is launched from the ground at an initial speed of 10 meters per second, its horizontal range r is given by r equals 10 sine 2 theta, where theta is the launch angle, measured in radians. Determine the value of theta that produces the maximum displacement. So maximum value for our range will be our maximum displacement, I guess. So let's see. Let's first talk about what's happening here. So if I think about this as being 90 degrees, or pi over 2, straight up, and this as being 0 degrees, or 0 radians, then I know that I'm going to launch my projectile somewhere in between those two angles. Because if I launch at 0, it's not going to go very far. And if I launch at pi over 2, that doesn't make a whole lot of sense either. So somewhere in the middle, we're going to get a good trajectory. So we're going to say that 0 is going to have to be strictly less than our value for theta, because we don't want to be exactly 0, which will have to be strictly less than pi over 2. So we don't need to worry about endpoints because there are none as such. So let's see what's going to happen here. dr over d theta will help us find our critical values, which is where this maximum or minimum value is going to have to happen. So if I differentiate 10 sine of 2 theta, I'm going to have 10 times cosine of 2 theta multiplied by 2. So I get 20 cosine of 2 theta. All right, so for critical values, I'm going to let that equal 0 and find out what's shaken down here. So dividing by 20 means I'm just solving a simple trig equation, cosine 2 theta equals 0. So let's think about that. 2 theta will have to have values of angles that make the cosine function 0. So on a unit circle, we should know that cosine will be equal to 0 at pi over 2 or at 3 pi over 2. And of course, any multiple of 2 pi added onto those will also get us some good gravy. So let's see, we divide everything by 2 here, and we're going to have theta equals pi over 4 plus any multiple of pi, or we're going to have 3/4 pi plus any multiple of pi. Now, that's a general solution for this if n is any integer. But we're not interested in any values. Remember, we restricted what theta had to be. So theta can't be less than 0, and it can't be greater than pi over 2. So adding multiples of pi to this is going to get us out of where we want to be. And 3/4 pi is already doomed, whether we add pi to it or not. So this is all gone. So the only possibility here is going to be at pi over 4, which if you think about it is going to make some good sense. So we want theta to be equal to pi over 4. That's going to be our value of theta that gives us our maximum value, because then we're going to launch at 45 degrees. This gets the projectile as far as we can get it. Okay, good question. Next one. A particle is moving along the x-axis, so its velocity is given by sine t plus cosine t. Okay, so sum of two functions. What is the particle's maximum acceleration? Ooh, tricky. On the interval x goes from 0 to 2 pi. So let's think about this. We've got a closed interval, so we'll have to check endpoints. But they tell us the velocity function is given. But what we want to do is we want to maximize our acceleration function. And if we want to maximize acceleration, we're going to have to get our critical values where the derivative of the acceleration is equal to 0. So we're actually going to have to look at the derivative of the acceleration, or the rate of change of the rate of change of the rate of change. So that's like a third derivative of the original position function, which we don't really know anyway. We just know the speed or velocity function, rather. Well, did you know that there is actually a name for the rate of change of acceleration? Yeah. It depends on which side of the pond you're on. In the UK, they call it, I believe, the jerk. But in the States, they call it the jolt. So, wow, cool stuff. All right, so let's get the derivative of velocity first to get an acceleration function. So acceleration is going to be v prime, which will be derivative of sine is cosine t, plus the derivative of cosine is minus sine t. And then we're going to have to get the derivative of the acceleration function. So a prime of t is minus sine t, and then minus another cosine t. So we get two negatives here. So we want to let that equal 0 and solve for our critical values. And once we have our critical values, we will compare them to our endpoints, and then we're happy. Okay. So how do we solve this trig equation now? Well, let's take the sine over to the other side, and we'll use a little bit of logic here. So if sine t is equal to negative cosine t, then what that tells me is that my sine and cosine are equal, but they have opposite signs, S-I-G-N-S. So let's look at a unit circle and think about where sine and cosine have the same values, but opposite signs. So this quadrant is out and this quadrant is out because they have the same signs, S-I-G-N-S there. But at these two places, when I'm at multiples of pi over 4, so this one is going to be at, let's see, 3 pi over 4, and this one is going to be at 7 pi over 4. Now, do I have to worry about general solution? No, because there's no complex arguments here. There's no arguments with any transformations, and we're restricted to 0 to 2 pi. So what we have to do now is check these two critical values as well as our two endpoints. So I need to know what's the acceleration at each of those places. So 0, I want to know the acceleration at 3 pi over 4, at 7 pi over 4, and I want to know the acceleration, last but not least, at 2 pi. Well, maybe it's least, I don't know yet. So acceleration at 2 pi. So let's see if we can work those out and come to a reasonable solution for this particular question. Let me see now. We're trying to find the values of these things. So we want the acceleration, which is cosine t minus sine t at each one of those. I'm not going to point you in the direction of the solutions yet because the solutions will give it away, but I want to make sure we work through this anyway. So let's see. If we're at exactly 0, we're going to have cosine minus sine. So at 0, cosine is 1 and sine is 0, so that would give us 1. At 3 pi over 4, cosine is negative root 2 over 2, and sine is positive root 2 over 2, so that would give us a total of negative square root 2. And at 7 pi over 4, the cosine is positive root 2 over 2, where sine is negative, so they'd add up to give us a total of positive root 2. And at 2 pi, cosine is going to be equal to 1, and sine is going to be equal to 0. So we have that much. So it looks to me like the maximum value of acceleration is here at 7 pi over 4. But if we look at what's happening over here, they give it to us in terms of the sum of the two trig functions that we had. And this is why I didn't want to point it out to you right away, but we'll look at this. There's only one of them that has a subtraction, which would say that's the only one that could be an acceleration. And in fact, it's true. It was at 7 pi over 4. So B is the answer. Oh. All right, next question is the your turn question. A particle is moving along an x-axis, so its displacement is given by a function. Nice. Determine its maximum speed and at what time or times this occurs. So good luck with that one. A little bit more optimization for you, and it combines optimization with rectilinear motion, two fun topics. So I hope you enjoy that. Here's a solution, all worked out in its gory detail. Should be nice and clear for you. And let's look at the highlights of some of the things that we saw in this particular session. For rectilinear motion, to relate velocity to speed, we say the particle is speeding up when its velocity and acceleration have the same sign and slowing down when they have opposite signs. So don't forget that one. We use sine graphs to determine the direction of motion and acceleration if we had to, but in this case we were able just to tell when it was positive and negative at certain particular values. And it says when motion problems are modeled by trig functions, there are, I should say they are, not there are, excuse me, well, they are likely, what a typo. So this should say they are likely, oh no, I'm incorrect, it was correct the first time. There are likely to be multiple critical values, excuse me. So by checking them all, as well as the endpoints, it's going to be critical for us to find our solution. Critical, like critical values. It's funny stuff. Good luck studying, hope everything's going well.